Before we jump into the deep neural networks and understanding how they actually work, I do want to talk about a couple of the limitations in this lecture, or this part of this lecture and the next one. So the big thing that you always have to be worrying about with deep neural networks is overfitting. And basically, the deeper that your network gets, the more likely it is to overfit. So I know that you've seen something similar to this already with maths. I'm just going to go back over this quickly to make sure that everyone is on the same page. So let's say in this case, let's say that the x-axis is age. And let's say that the y-axis is IQ. And this is going to be the distribution of our data. So the blue dots are going to be the training data. And the test data is going to look something like this. Right. So we can see that the actual distribution of our data is going to look like this red line. Okay. And in the videos I've done so far, I've talked about this red line as something called f star of x, which is the perfect real world function. And our neural network is going to be the blue line, and that is going to be f of x, which is trying to approximate this red line. So we want the blue line to be as close to the red line as possible. So underfitting happens when the model just doesn't understand the data at all. Overfitting happens when it understands the data too well. So yeah, here all I've done is this is the initial distribution, and let's say that we pluck out these red dots. We're going to use them for the test set, and the blue dots are going to be for the training set. So this is what our model should look like, and you'll see that when we test on these data points, there's going to be, like, it's not perfect, but we can do a relatively good job. But when we try and do this, when we try and test on the model that is overfitted, we have a big problem. So this here, we can see when you're talking about like a 10-year-old, they've got an IQ here. But now the model is coming right the way down and across here. So it's going to think that people with an IQ of, or people with an age of 15 or 20, 25, they have an IQ of 0. And it's only when you get back up to being 30 years old that you regain your intelligence somehow. So obviously this is a massive failure case and something we really need to protect against. And what is most likely to be happening here is that the network is just simply far too deep for the data that we've got. Maybe we don't have enough data to train a deep learning model. So because we have too many of what's called parameters, because we have too many parameters in the model can perfectly memorize the data that it's seen already. So it doesn't actually perform well on any new data because it's just memorized the data it's got and isn't interested in anything else. This is kind of similar like when you're at school, you did your GCSEs, A-levels, BTECs, whatever. And if you just, like the week before the exam, you go through all of the material that you've seen throughout the course and you nail the exam, everything's gone well, but the day after you've pretty much forgotten everything. You can't apply those concepts you've learned to the real world. You've just memorized them so that you can pass the exam. That's essentially what a machine learning model is doing when it's overfitting, and it's extremely common with deep networks, particularly the very deep networks that we're going to look into in a later lecture. So there are a few things that we can do about overfitting as well. The most obvious ones are to, well, simply use less layers and use fewer neurons per layer. And I'm going to talk to you exactly what that means later on. There's also something called dropout, which I'll discuss in lecture 5. But what I want to draw your attention to first is that we can actually do something a little bit different when we design our train and test setting, and to help us to spot overfitting earlier. So instead of having just a train and a test, we can take the test set. So let's say if we have train is 90% and test is 10% of the data. We take this training set and we split it again into a new train set and a validation set. So I will take, let's say that this is 80% of the total data, and then the validation set is 10% of the original data, and we still have the exact same test set. So this validation set will now still be in the same positions on the distribution, but we can actually see this validation set while we are doing training, and we can test on this. We can essentially simulate the test set by using this validation set. So we can spot any problems with overfitting a lot earlier. The other thing that I think is really a massive problem with deep learning models, machine learning in general, but you see it quite a lot with deep learning because models are so good at memorizing this distribution, is that they really struggle to generalize to new data sources. So you can always think of this as overfitting on the initial distribution, which makes them worse at being useful on new sources of data. So let's say you've got, let's imagine that this distribution that we're looking at here is age versus IQ for one country, say the UK, but for a different country you might get a new distribution which is instead like this. But because the model has done such a good job, maybe I should do it on this one. So if the model has done a really good job of learning the distribution that it's already seen, it can then become very bad at learning new distributions. And this is the case throughout natural language processing. In medicine is really important. It's also the case in computer vision. So I personally worked on re-identification, which tries to solve this, or tries to be a little bit more robust against this. And on one data set that's collected in Hong Kong, if you train on that data set but then test on a data set from America, you get really shocking results. You can get 90% performance on the data set that you've trained on, and then only 10% performance on the new data set, even though for a casual observer you can't really see any difference in the data set. There's just some underlying noise, maybe from what lens the camera uses. It might be some very slightly different lighting conditions that the data is captured under. But these very small things that humans can't really perceive can make a massive difference to artificial intelligence or deep learning models. So essentially, what I'm saying here is if you train a data set on 90% of the works of Shakespeare, and if you then test that model on just Romeo and Juliet, you will get very good performance. It will do well what you want it to do. But if you take that same model and then apply it to Donald Trump's tweets, then it's not going to do as well.